Hello everyone, this is Tasaki. Welcome to my online lecture. So today I'm going to talk about our own work on heat engines, but this lecture should be understandable to anybody who has some idea about thermodynamics, okay? So I thought it would be a good idea to start the video by showing you some demonstration. So I found this at home. This is called the Stirling engine. You'll see this, okay. The Stirling engine. And of course, this is a kind of toy version of Stirling engine. And this is from a Japanese company called Gakken. And this is beautiful and I like it very much. So if you place this on something hot, like cup filled with hot water or hot coffee or whatever, and if you put it like this, and if you wait for a while, it starts rotating by itself. It's an engine. To be more precise, I have to say that it used to start rotating. And after some years, for some reasons I don't understand, it doesn't work anymore. But trust me, it really worked. So if you go to the web page, which is linked from this video to my web page, and then you will find a link to a YouTube video in which they show the same thing, basically the same thing in motion. So if you're interested in, please take a look at that. And anyway, okay, let's start. So let me first say a few words about thermodynamics. So what is thermodynamics? I would say it's a quantitatively exact macroscopic theory, which tells you about possible transitions between equilibrium states and also energy transfer associated with these transitions. This is a quote from a famous paper by Elliott Leap and Jakob Ingvason, and they say that the second law of thermodynamics is something really exact. And if you can violate the law, the second law, in a reproducible manner, then you will be very rich, and also you will get a Nobel Prize, and of course you will change the whole civilization. But probably that's impossible. And another important fact characterization about thermodynamics is that it is formulated entirely within macroscopic description without reference to any microscopic world. And this is a reason that thermodynamics was a crucial guide in the revolution of physics from classical to quantum mechanics. So probably you know that in the beginning of 20th century, there was a revolution which shifted from classical physics to quantum physics. And Max Planck and Albert Einstein and many others who led this revolution were indeed guided by thermodynamics. That's quite interesting. Okay, thermodynamics is quite an old field and was completed a long time ago, but there are still some new progress in the way we understand thermodynamics. So this is a famous paper by Leap and Ingves in 1997, and this is a very difficult mathematical physical paper. But anyway, in this paper, they give rigorous operational formulation of thermodynamics, which also has a deep physical insight. So do you remember the definition of entropy you learned in your college? Actually, this is the definition given by Leap and Ingves, and this is only one-line definition, which is beautiful and which is elegant. I won't explain this, but this is something very important. And actually, this paper was a shock to many of us. And especially in Japan, this paper led to the publication of modern textbooks of thermodynamics, which are written from fully operational points of view. And in my opinion, which are very clearer to understand. So actually green, red, yellow. This one is by Akira Shimizu, my friend, and this one is by Shinichi Sato, my friend, everybody's friend, and this is by myself, and it's called Netsurikiraku Gendai Teki na Shiten Kara. But all of them are written in Japanese, and I'm sure that most of you do not read Japanese, but here's the good news. So myself and my co-author, Glenn Packett, are now working on extended, improved version of my book course, in English, and now Glenn is working. I hope Glenn is working on the final version. So we expect this book to be published from Oxford University Press like this year. Okay, so please wait for this. Okay, so let's move on to the motivation of this work. So we are interested in heat engine. What is heat engine? It's a central object in thermodynamics, and it is indeed it's a physical system which converts heat into work. What is heat? Well, this is the definition. It's a non-mechanical transfer of energy, but you can think of it as simply as a non-usable energy, and work is usable energy. So if I say that something converts heat into work, what you first imagine is something like this. So here's something hot, and this machine takes heat, and energy must be conserved. So this energy in terms of, in the form of heat is converted into work, and this weight is raised. Or this is more convenient. Here you have hot water or hot room or whatever, and this miraculous machine cools down the water or the room, and then it takes some energy in the form of heat, and then this energy is used to charge your iPhone battery. And this is very nice. I mean, in hot day, you can cool your room and also charge your iPhone batteries. But they look nice, but they cannot be realized. These are something called perpetual mobile of the second kind, and such machines are inhibited by the second law of thermodynamics. So probably we can never make such machines. Engines which are possible looks something like this. So to be precise, I'm considering now something called external combustion engine. And these heat engines operate cyclically, in a cyclic manner, interacting with two heat paths with different temperatures. And in a single cycle, this heat engine absorbs energy QH in the form of heat from the hot heat path and expels energy QL to the cold path. And since the energy must be conserved, this difference W is extracted as useful energy work. Okay, so this is a schematic picture of a heat engine, and I'm sorry, instead of using temperature, for some reason, I'm using something called inverse temperature. This is more convenient in statistical mechanics. So I use this. So this inequality says that beta H is smaller than beta L, but this is inverse temperature. This means that this one is hotter than this one. Okay. So of course, this is not a fictitious thing. So these are useful things, and there are many realistic external combustion engines, heat engines. So the Stirling engine is one example, and the Thomas the tank engine is an example, and also a coal-fired power plant. These are all examples of external combustion heat engines. Okay, so there are two quantities, efficiency and power, that characterize a given heat engine. What is this? So let's consider a general heat engine and attached to two heat paths. So this is a picture, and this is a work extracted. Efficiency is simply defined by this formula. It's W extracted work divided by QH, the absorbed energy. Okay, so this is really efficiency. And by definition, it never exceeds 1. And of course, you want to have an efficient engine, and you want this ratio to be as close to 1. But that is impossible. So back in 19th century, nearly 200 years ago, Carnot found that there is a fundamental universal upper bound for the efficiency of a heat engine. No matter how clever you are, no matter how skillful you are, the efficiency of your heat engine can never exceed this quantity called eta C, the Carnot efficiency, which is given only in terms of the temperatures of the two heat paths, and that it's strictly less than 1. So, okay, so no matter whatever you do, the efficiency of your heat engine cannot exceed this thing. That's the efficiency and the universal bound. And this bound is very important. Actually, it's at the heart of thermodynamics. Okay, so what is power? That's simpler. So let tau be the period of this cycle. Okay, so, and W is the power obtained within this time interval. So W over tau is the, W is the energy, the work. And so W over tau is the power of this engine. And of course, you want to have an engine with higher power. And is there any limit like this for the power of a heat engine? Actually, I'll come back to this, but in thermodynamics, there is no fundamental limitation on the power of a heat engine. Okay, so since we don't have any general result, let's take a look at an example. And of course, the most basic example of a heat engine in thermodynamics is the Carnot cycle. And probably you learned about this. So it consists of one isothermal process in which the engine interacts with this hot temperature heat bath and an adiabatic process, and the other isothermal process in which the engine interacts with the cold temperature heat bath and another adiabatic process, and the whole thing forms a cycle. You can repeat this. And as you learn in school, if you compute the efficiency of this cycle, you find that it is exactly eta C. So this is the maximal possible efficiency. This is quite nice. It has a very high efficiency. But the trick to get this high efficiency is that you use quasi-static process here. It means you do it very slowly, infinitesimally slowly. So the ideal Carnot cycle is realized only in the limit where the period becomes infinitely large. That means since W, the work is finite, W over tau should vanish in this limit. So the power is basically 0. So the Carnot engine is extremely efficient. It has the maximal possible efficiency that is allowed in this world, but it's totally powerless. Okay. So this observation leads us to a fundamental question. Can there be a heat engine with non-zero power, which still attains the maximal Carnot efficiency? So let's take a look at some examples. So, okay, so here, this engine took quite a long time because it's very close to equilibrium. So for example, here the temperature of the heat bath and the temperature of this engine are the same. And that means that the heat flux from here to here is infinitesimally small. So if we want to speed this up, probably it's a good idea to make a temperature difference between here and here. So make the temperature here slightly lower than the temperature of the bath. Okay, so that's done here. So I want to consider a slightly faster version of Carnot cycle. So this is a perturbed Carnot cycle, near Carnot cycle. And as I explained, I want to have a small temperature difference between the bath and the engine. So in this case, plus delta beta. Again, this is an inverse temperature, the inverse temperature. So this means that this one has slightly lower temperature. So there will be a finite heat current here and a diabatic process. And here you make the temperature of the engine slightly higher than that of the bath. And so there's finite heat, non-zero heat flux like here, a diabatic process, and this thing repeats, okay? Now, what is the maximum possible efficiency of this near Carnot cycle? Well, I think you can easily convince yourself, but that the maximum possible efficiency is given by this formula. This is the Carnot efficiency, but with these temperatures, inverse temperatures, replaced by these slightly modified temperatures here and here. So this is the formula. And if you assume that delta beta is small and expand, then you see that the efficiency, there is a loss. There is a loss in efficiency. Efficiency goes down by this amount. Okay. Right, but anyway, let's look at the minimum possible period. Since you have to carry this amount of heat between uh, engine and heat bath, and this is heat current, so this is the minimum possible time needed to operate this near Carnot cycle. And I also assume that this heat current J is given by this formula, where delta beta is the temperature difference and kappa is something I call heat conductivity. So if I plug this in here, you get this formula for the minimum possible period. Okay. Now I have two formula with this delta beta, so I can eliminate delta beta and get a relation between tau and eta. Okay. Tau is roughly approximately given by this. So this is just a rough approximate calculation. Okay, anyway, then if you look at this, and if you want your efficiency eta to be close to eta C, then you will find that this guy is small and this guy is big, so this whole thing diverges. So this means that if you want your efficiency to approach the Carnot efficiency eta C, this power must vanish. Okay. Well, this sort of suggests general rule, but anyway, this is only an example. I mean, we started from something we understand very well, the Carnot cycle, and we just perturbed it a little bit. So, well, this is just one example of non-Carnot engine, and you can imagine many other possibilities, like using non-equilibrium phenomena or in applying magnetic field and so on. So we have to answer a question, a general question. Can there be a heat engine with non-zero power which attains the maximal Carnot efficiency? And as I said before, thermodynamics alone cannot answer this question. Why? Well, if you look at the standard theory of thermodynamics, it has no notion of time scale. So it only tells you which transition is possible, which process is possible, but it doesn't. Thermodynamics doesn't tell you how fast you can do or whatever. So we need some microscopic dynamical framework to discuss time scale, and many, including us, take approach based on non-equilibrium statistical mechanics. So here are previous works back in 2016, and there are many works more. And after that, after this, I think there are much more, many papers. And so some say no, some suggest yes based on some calculation, and some suggested yes, and so on. But anyway, we had rather definitive result here. So let me explain our result. And so this is a joint work with Naoto Shiraishi. He's a young guy, and he was a postdoc at Keio University when we did this together, but now he is my colleague at Gakushin University. And this is KG Saito, and of course, this is Hal. Okay, so let me explain you our setting. So we take statistical mechanical points of view. So that means that we imagine that our engine consists of some small molecules or whatever. So here I model the engine as a classical system of n particles. N can be huge, 10 to the 20 something, and with arbitrary potential and interactions. It's quite arbitrary. And so it's described by a huge Newton equation, but we also have to take into account the effect from the heat mass. The effect of the heat mass on the dynamics of the engine is described by random force using the Langevin type formalism. Well, this is a very standard formulation for treating noise from heat mass. And this is also important. We want to consider heat engine. That means this kind of piston shouldn't be moved properly. You push it, you press it, you pull it, and so on. And also here you connect with this heat bus, and then you disconnect it, and you connect with this, and so on. So we assume that there is an external agent who controls the potential and the interaction with the bath in a periodic manner according to a fixed protocol. So this guy knows how to push piston, how to, connect this, disconnect it, this, and so on. He has a scenario, which we call a protocol, and he does it in a protocol, in a periodic manner. And I say that this is a very general and standard framework that can describe any macroscopic engines. Now, with this formulation, we answer this question: can there be a heat engine with non-zero power which attains the maximum Carnot efficiency? Our answer is no. Of course, provided that our description is valid. And this is our main result. Okay. Tau is the period of this arbitrary engine, and eta is the efficiency of this engine. Eta C, of course, is the Carnot efficiency, and QH, QD, these are heat, and this is inverse temperature. The only quantity I have not explained is this theta bar. And this is a finite quantity which depends on the state and the design of the bath. But let me say that if the system is very close to thermal equilibrium, then this theta bar is equal to this heat conductivity, thermal conductivity that I talked about before. Okay, so it's a very natural quantity, it's basically thermal conductivity. Okay, and actually from this inequality you can get this one, but I'll talk about this later. Previously, we considered the near Carnot engine and obtained this approximate formula for approximate relation between tau and eta. And if you compare this and this, they look almost the same, and especially when the system is close, engine is close to thermal equilibrium, you can replace theta bar by kappa. So actually, this one and this one are the same. So it means that we have, this is a rigorous inequality, but our inequality is sort of optimal. We cannot improve this. You cannot like say, well, we can multiply this by 2 and it holds. No, it doesn't. So this is a multiple inequality. Okay, so this is a consequence of this inequality. This one is a consequence of this inequality. So let's take a look at this thing. Okay, so this inequality relates the power to the efficiency. So here's a two-dimensional plot of efficiency and power. And of course, you want an engine with high efficiency and high power, so you want something here. But already back in 1823, Carnot said that engines in this orange region is just impossible. You can never make any engine here, okay? So you have to give this up. And our new result said that engines outside this parabola is just impossible. The only thing we can realize is under here. And you have seen this already. And so if you increase your efficiency towards this eta C, the upper bound, the possible power goes down. And so this means that efficient engines are just powerless. Okay, so if you want to have an engine with Carnot efficiency, then it has power 0. Okay, so here's summary and remark. So we have proved a trade-off relation between power and efficiency, which implies that a heat engine with non-zero power can never attain the Carnot efficiency. And if you look at the proof, inevitable loss in a heat engine with non-zero power is caused by heat current between the engine and the bath. And the story is basically the same as what we have seen in this near Carnot engine, okay? And I can say that, oh, this is a fundamental limitation on external combustion engines, including the Stirling engine, Thomas the Tank engine. But if you look at the internal combustion engines, like engines that we have in our cars, then there's no such problem. So I think this partly explains why we do not drive a car which has Stirling engine on it. Okay. That's basically all what I wanted to say. Thank you very much for watching. And actually, this video has part 2 in which I explain in detail the formulation and the proof. So if you're an expert and if you're interested in, please also look at video part 2. Okay, thank you very much. Goodbye.